let's have a look now at calculating the surface area of a prism. So first of all, what do we mean by the surface area? So the surface area, again, it's a two-dimensional idea. So if that was, say, a prism, I'll use this calculator here as a prism, or actually any 3D shape for that matter, but we're just focusing on prisms at the moment. The surface area is only the outer surfaces, okay, the exposed surfaces. We don't care about what's inside. So another way to think of it is the area of its net. Okay, so surface area can be thought of as the exact amount of wrapping. So think of wrapping a Christmas present, for example. Think of the exact amount of wrapping needed to cover every surface of the prism. No more, no less. Okay, that would be also the surface area. Some prisms may be open at one end or both ends. Okay, so open ends are not included in the surface area calculation. There is one example that has an open end, so we'll look at how that works. So just quickly, I'll demonstrate what I mean by the net. So you might have done these some time ago, and I might just move this out of the way and see if this is going to work. Okay, hopefully it will. Alright, so here's an example of a rectangular prism. Okay, it's a bit wonky, but anyways, so that's a rectangular prism. If I was to open it up, what would it look like? Okay. Okay. So they would be the ends. Okay, that would be the ends. So I'm just opening it up basically, and I'll need to add a few extra sides, obviously. So that side goes there. Okay. Alright, that side goes there. And maybe two more of these. So that goes there. Okay. That goes there, that goes there, that goes there. And that would be the net of the rectangular prism. So what's its surface area then? It would be the area of 1, 2, 3, 4, 5. We're missing one more. Okay, which side is missing to make the complete net? In fact, this would be the net of a rectangular prism with an open top. So we would need one more of these bigger rectangles. So the complete net of a closed rectangular prism, okay, I need to add one more, okay, one more of these. So I might just move that up a little bit, and okay, so I might just use these red ones. Yep. Okay, and this would be the complete net. Okay, so once you start to fold that up, okay, you can see how it comes together to form the three-dimensional shape. Okay, it's not going to work fully here or come as I would like it exactly, but you get the idea hopefully. So folding that back out, okay, actually magnetic, so they're a little bit tricky, and okay, I think it's kind of falling apart now, but anyways, okay, hopefully you get the idea by now. Alright, I'll just draw part of it again. Okay, so in other words, surface area, imagine you can fold it all back out. There's a few parts of these missing, obviously. It'll be the total area, okay, of its net. Now, let's have a look at some examples. I'll move all this away. Okay. Now, if you like, at this point, you can pause the video and have a go at calculating this for yourself. And I highly encourage you that any of the videos that you watch, before I actually start working out these examples, pause the video, spend 5 minutes or so, and see if you can work it out for yourself. Okay. Also, look at how I set it out, and I think that's very important. The organization of your working out is critical. Okay, it's not one of those optional things that you could just write it everywhere. Organization is key. That's where mistakes are made, most likely. When you're under time pressure and the working out is everywhere, you really run the risk of losing precious marks that ordinarily you would not lose. Okay, all right, let's have a look at the first one. We have a triangular prism. Okay, so we've got the two triangular faces and we've got some rectangular faces there as well. So we've got the front and the back, they're identical. Okay, so we don't have to calculate these separately. Being a prism means you're going to have some symmetry, which is really nice. You don't have to replicate the same calculation. Okay, so let's do that, and that's easy enough to do. Just thinking forward now, we have a rectangle at the bottom, okay, which is 6 meters by 20 meters. So that's the bottom surface or the base surface. We have the left hand and the right hand surface as well. So we're going to assume that these are equal length. I should have probably put that earlier, but just assume they're equal length. If we assume that, that's fine. How do we find the left and right rectangles? Because we need this side here. We need side x. Okay. So if you're starting to think, well, okay, can't do it. Think again. Where can you see a right angle triangle? Okay, here it is. Which means that we can use Pythagoras Theorem to find this hypotenuse. All right. Now the base is split in half, so this would be identical as well because it is a isosceles. It's an isosceles triangle, and the height of an isosceles triangle will divide the base in half. So that means that that's going to be 3 meters, and that's also going to be 3 meters. All right. And if you know Pythagoras Theorem well, I hope you do. 3, 4, 5. Okay, 3 squared plus 4 squared equals 5 squared. Okay, so x squared is equal to 3 squared plus 4 squared. That's a 3, 4, 5 triangle. Okay, x squared is equal to 25. Therefore, x is equal to 5. So we do have a value for this hypotenuse. Now we have enough to be able to work out the surface area of this triangular prism. So what I'm going to do, I'm going to set it out like this, right? Front and back, right? You can vary this. I'm not saying you have to do it exactly like this, but just keep it organized, however way you want to do this. So front and back, okay? They're triangles. So let's work out the area of one triangle. Half base times height, half times 6 times 4. But because we have two triangles, let's multiply that by 2. Okay? And that's going to equal 24. Okay? I'm not going to write the units. There's no need. I'll just write it at the end in the conclusion. Now, we've also got the left and right rectangles that are identical as well. So again, no need to work out each rectangle separately, unless of course you have to. Okay? So left and right. Okay, they're rectangles. It's going to be 20 times 5, and we have 2 of those rectangles, and that gives us 20 times 5 is 100 times 2 is 200. Now it might also be a good idea at this point to just underline these subtotals, because in the end we're going to add them up, and when you're under exam pressure and you're sort of having to work fairly quickly, and this is where organization is so important. You can see what you've calculated, and it's very easy to see what you need to add together. Now, the base is just a single rectangle on its own, okay, and that's going to be 20 times 6, which is equal to 120. So the total surface area, we just add them up. That's our total area, okay, is equal to, and I should, in order to keep to what I've said, which is underlining the subtotals, we just add up what's been underlined in blue, right? 24 plus 200 plus 120, which equals, what do you think? 320 plus 24 is 344 square meters. Okay, think I've got that right? Yes, I do. All right. Hopefully, so far so good. Now let's have a look at part B. Part B states that what we have is basically like a drinking trough or a feeding trough, but we're told that it's open on top. Okay, so again, what does that mean? Okay, it means that what we're going to do, we're going to calculate these areas, but we're not going to include the top there. Okay, so once again, I want you to have a think about this carefully. Okay, now there's something else I'm just going to add to the diagram to make it a little bit easier, and something I didn't actually, I omitted before when I was transcribing this question. We need the these or basically these diagonals or these oblique lines there, so the sides of this trapezium. I'm just going to work them out. I'm just going to pause the video and I'm just going to work them out and add them in just to make it a little bit easier. Okay, so this was omitted before, but I'm just added it in now because the question was originally a little bit harder. You had to use Pythagoras Theorem again, so I've just altered this slightly. It's just for the principle, just so you know what to do here. But I have calculated it to do 2 decimal places. So if it's 7 meters on the top, 4 meters on the bottom, that means that there's 3 meters. There's basically 3 meters extra on the top, 1.5 meters. It's a trapezium that has an axis of symmetry, so it's identical if I was to flip it over. And using Pythagoras Theorem, if it's 5 meters high and 1.5 meters across, then the hypotenuse must be around 5.22 meters. So let's stick with that. Again, let's do what we did in part A. Okay, and might use a different color pen this time. All right, so we got front and back. Okay, and they are trapeziums. So we're going to take the average of the top and the bottom, okay, the parallel sides. So 7 plus 4 over 2, multiply it by the height of the trapezium, which is 5, and there are 2 trapeziums. Okay, so 5 times 2 is 10, which is really nice. 7 plus 4 is 11. 11 divided by 2 is 5.5. 5.5 times 10 is 55. Okay. And again, let's underline these subtotals. Okay. Now we've got left and right. Okay. Again, a bit like the last example, but just a different shape. But just has one side missing. Okay. So left and right, we've got left and right identical. 5.22 times 13. So that's that rectangle here. Okay. 5.22 times 13, and we've got 2 of those rectangles. Okay. So typing that in, 5.22 times 13 times 2. We've got 135.72. And lastly, right, we have the base, which is 4 times 13, which equals 52. Okay. Lastly, let's add these all up. Again, just to make it easy to see. I'm just going to use a different color pen again. So total area, and we're just going to add what's been underlined. So right, 55 plus 135.72, okay, plus 52, okay, and we get 242.72. and that's square meters. Okay, so 242.72. Okay.